Okay, so it's my pleasure to introduce our guest for today, who it's a particular pleasure for me because Adrian was my, I guess, commilitone is the Swiss word. We were classmates in the period that I did my doctorate at Columbia University, where he also was engaged already as a head of the lab at that early stage, eventually receiving his PhD in engineering materials diffraction and structural health monitoring in 2017. After which point he also assumed the head of the lab position of the Carleton laboratory at Columbia University, where many of the activities initiated during his PhD took, I guess, full form. And now he will be explaining or going a bit more in depth as to what these activities are, and including also exciting collaborations with Oak Ridge Lab, as far as I understand. And this is all in the theme of neutron scattering, but you would also be giving us a broader perspective on future directions of the topic. So I will give you the floor, and we look forward to hearing.
Thank you, Eleni. And one more sound check to those who have joined on the internet. I hope you can hear me. Excuse me. Es freut mich außerordentlich, hier zu sein, vor allem auch in der Schweiz als Schweizer, auch wenn ich jetzt schon für längere Zeit in Amerika weile. Und nochmals danke für die Einladung, Eleni. But I will hold this talk in English for the sake of all involved. So it is my pleasure to be here, and thank you again for the invitation, Eleni. What I will speak to you today about is essentially what I've been doing for the last few years, and also some details on a new engineering materials beamline that we are designing right now at Oak Ridge National Lab. It is an open beamline that will be available for research both internationally as well as nationally. So if you are interested in pursuing some of these tools, then this is something that you as a scientist can use for free on the US federal dollar. And there is no discrimination between international and national users, which is relatively refreshing for once. So to give you a quick introduction, I will speak just about neutron diffraction and imaging and what I've done, where I come from. Eleni already mentioned that I started at Columbia and I'm still there, but I'm branching out, of course, to some of the national labs. I'll speak about the new beamline, the capabilities, what brought me to neutron diffraction as a civil engineer. It's not a common direction, obviously. Then just a fun example, and I really mean for this whole talk to be relatively laid back. It's a lunch talk, it is summer, right? So you won't see any equations, almost no equations. It will be just sort of a fun show and tell. And then of course, also where we are with this beamline development, and then looking ahead, using these capabilities, especially in the engineering world, and especially also since I am originally started in structural dynamics, I also want to use this for some level of forensic engineering quantification of, for example, failures. So a little bit about me. I came to Columbia University in 2000, which is already a while ago, where I did my bachelor, master's, and started my PhD. And then the department decided, since I was working in the lab on the shake table that Eleni spent some time on as well, she remembers it well, I think. I took over the lab, which looked like this when I took it over in 2007. And now it looks like this. So the good thing is that, yes, better than 2007. And this is a typical classical structural lab, materials lab that you would find. It's sort of an IMPA style lab in that we do standardized testing for industry and for the state, but we also, of course, support the research of the department. So now that things are running a little better than they used to, I, of course, also have more time to do what I want to do, which is partially, there we go, partially looking at materials with advanced methods and looking through materials. So through that, through my PhD studies, I started working at various national labs, and I'll show you sort of how I stumbled into that. Now, as a civil engineer, you have it very good here in Switzerland, because in the US, the infrastructure looks like this. This is a real photo of an in-service bridge, the Williamsburg Bridge in 1988. This is supposed to be the web of a structural girder. It is suffering from non-existence, so it's relatively unhealthy. This bridge was actually condemned in 1988 because it had a safety factor of 1.2. But it was quietly uncondemned 3 weeks later because the city noticed that essentially you could not live without this bridge. So this is where the concept of the irreplaceable infrastructure was born. It's true mostly for highly urbanized areas. If you are looking at New York, if you look at Hong Kong, anywhere else, to build a new structure in an area that is already fully developed is incredibly difficult unless you tear down the existing structure and you rebuild it. That will mean that you will lose the structure for a few years. If you build a new structure next to it, then you will have to raise multiple city blocks, which is generally also politically and socially untenable. So this is where I started, and I said, well, we can actually look at failure cases and look at the mechanics inside these systems relatively well using neutron scattering. Now, just to give you an idea, this is 1988, same bridge now in 2013. This is considered acceptable in the US, so we're good now. Looks great. Now, if we look at and this is where my PhD sort of took a turn. He said, well, if we look at a suspension bridge cable, right, what is it? It's a highly parallelized system with maybe 6,000 to 25,000 5mm steel wires. We look at each one of these groupings called strands. They're essentially just 127 round 5mm wires in hexagonal packing. There's no spin, there's no lay to this cable. It's purely just compacted mechanically using hydraulic compaction. So what happens if I take a bridge that has not been well maintained, that has maybe not been, for example, air conditioned? So cables today, drying the air is very popular, but in New York City specifically, the initial approach was actually pouring oil into the cable. So oiling the cable to fill the interstices, which are between 9 and 20% of the cable with oil. This was first whale oil, then linseed oil, and later petroleum products. Problem with linseed oil and whale oil is that they are volatile and flammable. So the Williamsburg Bridge cable actually caught on fire during oiling. It spontaneously combusted on a hot summer day. And then also the linseed oil is chemically volatile, so it leaves behind a wax residue, and it shrinks as the volatile organic compounds diffuse. So then you have essentially a waxy cable that you can no longer easily air condition because you filled it with something. So then the question is, if I have a wire break in a cable, when does that wire regain service load from its neighbors? Right? It's a very simple question, but it's fundamental to understanding the health of a bridge. You can imagine the two limit cases, right? If you have a natural fiber rope, so say a hemp rope or a sisal rope, no single fiber in that rope spans the entire length of the rope, obviously. So that means that all of the carrying capacity is actually transferred through friction between the specific fibers. So on the other extreme, of course, if I have a cable that is not well compacted, then that single wire might not regain load over a very significant length of the cable. And if a cable is 1 kilometer long, then if that is a significant enough length, then we may actually have a problem if we have an area with high corrosion. Normally this happens in very concentrated sections of the cable. So then the question is, what is my development length? And what is what we would define as the stress transfer factor eta, which is just the stress in that wire compared to the average stress in the cable. Now, the development length historically was just defined to be 2 cable spans, so 2 panels. Now, this was a committee decision after the Williamsburg Bridge incident, but it was never retested or never experimentally verified since suspension bridges have been built. So this is what I set out to actually answer as my PhD. And I said, well, how do we do this? How do we look inside a cable strand without disturbing it? So do essentially a friction analysis, a contact analysis without disturbing the section with instrumentation. Well, we can do this with neutrons. So we have a number of accelerator as well as reactor sources in the US. I mean, we also have the PSE here in Switzerland, but this is Los Alamos National Lab on your left, and then we have Oak Ridge National Lab on your right. I started my work at Los Alamos because that was at the time where we had our relationship. So what do? Well, we take a sample. So let's say we take a 7-wire strand, the simplest unit cell, where we have 1 wire in the middle surrounded by 6 wires. We can put those into an engineering materials diffractometer and then have a neutron beam come in. That neutron beam hits the cable. Some of it is absorbed, say 30%. Most of it is transmitted, and then a small percentage, a few percent, scatter. They interact with the neutrons actually interact with the nucleus of the various phases of the crystalline material that makes up the wire. So what is steel? Right? It's a polycrystal made up of various phases. So what we actually get from that is elastic strain, or at least a lattice parameter of our atomic spacing directly. And we actually get 2 scalars. So the most important takeaway here is that we're actually capable of measuring within a gauge volume, a little cube inside the cable, 2 elastic parameters of our crystalline structure. And now if you can imagine doing a D0 measurement, a baseline measurement somewhere, then we can also, between 2 stress states, actually get a relative strain. And we can do that inside a cable. So we can penetrate about 15 to 20 millimeters of steel without, again, mechanically interfering with the material. We can also penetrate about 100 to 150 millimeters of aluminum and measure inside an aluminum monolith, for example. And water is actually much tougher because neutrons are heavily attenuated by water. So, as I've already mentioned, essentially what we do is, and if you're a structural dynamicist, it's all sort of the same thing. It's essentially just the least squares fit. But what we do is we irradiate a crystalline set of unit cells. And from that, we get what we call, in this case, this is time of flight neutron diffraction. We get a time of flight spectrum. And each one of these peaks is actually the delay of those neutrons by interacting with a specific atomic lattice direction in the constituent material. So effectively, if we just do a nonlinear least squares fit of that, called Rietveld refinement, we get a lattice spacing. Now we can take that same material with those unit cells and deform it and irradiate the same point again, and then essentially get a second lattice spacing. And from that, we can get lattice strain. So that's essentially the method of traditional neutron diffraction. And this is the bread and butter of what neutron scattering people do, especially in the engineering world. Of course, we can also get an error. So this is fun. This has been done now for 30 years. But of course, the issue is that we only get that measurement in 1 gauge volume. So it's literally a little cube or cuboid inside the material. And for us to understand a larger 2D or 3D specimen, we have to actually step through the material and measure at various points. And that can take minutes or hours per point. So it's quite tedious and quite slow. So if you want to do dynamic measurement, this is very tough. You can do dynamic measurement of 1 spot only. So what we did here is, you can see the wire strand here in the diffractometer. We essentially broke the center wire, then under various confinement loads with a clamp, we actually measured the load pickup of the center wire through that clamp. So we now have essentially a friction coefficient as a function of confinement through that clamp. So that was step 1. But of course, that begged the question, what does this mean in real life? What is my confinement in a real cable? Can I assume a mean field distribution throughout this contact regime? And that's actually a much more difficult question than we thought, because when we measured it, this is some of the final results from some work a couple of years ago. You can see that we are now looking at the confinement forces, the forces in this plane, essentially the compression forces on the specific wires, the 61 wire strand, and you can see that it's a relatively chaotic system. We have certain wires that are under heavy compression. In this case, these are von Mises stresses. Other wires that are almost unstressed. No, it'll come back. So here, what we actually posited in the end is that this is a function of the diameter compatibility or incompatibility of the wires, because the wires have about 15 microns of tolerance in production, and that is sufficient in this relatively tight packing regime to actually cause this huge chaotic behavior. So this is now a problem, because now we are looking at a stochastic field instead of a prescribed mean field distribution, where we say, well, this cable, we can assume this is the compaction, but it's truly not that simple. So this is how I came to neutron scattering. But recently, we've actually now at Oak Ridge National Lab, I have a colleague, Adrian Brügger, who is commissioning a new imaging beamline. And this is essentially the future of where we are going. Because if you think of X-ray technologies, we've long moved away from just doing X-ray diffraction. We are now doing X-ray imaging. It's very common, right? Everyone probably has had a computed tomography scan, and a tomogram is effectively just 3D X-ray imaging. And today we're also empowered by, for example, machine learning and AI to be much more efficient in how we can build these computed tomograms. And I recently also won a project to actually build, or first design and then build, a beamline at Oak Ridge National Lab. And this will be the first dynamic imaging beamline for neutrons at a Department of Energy lab. And I'll now go into some of the details of what this really means and how this can also be very interesting for you guys. Okay, so essentially what Oak Ridge did is they said, we're building a new source. This source will provide us with an incredible flux of cold neutrons. You can see up here, CUPI²D, that is the new beamline, has a flux that essentially is above everything else in the world that currently exists. But what does that really mean? Well, it means that we can actually do measurements. You can imagine now we are looking at an area detector. So just like a photoplate or just like an X-ray tomography detector. So you're looking at essentially a photodetector that detects neutrons instead of photons. And with this domain, or this source of neutrons, what we can do is we can actually measure across multiple length scales. We can measure on the atomic scale to get an equivalent measurement of what I've shown with neutron diffraction, but in this case, imaging, where we get one scalar strain through the sample for every picture that we take. We can do grating interferometry, which I'll also show in some more detail, where we're actually doing small angle neutron scattering using diffraction gratings. So we can look at defects, and we can tune our gratings to detect defects such as porosity, for example, in material. So we can measure porosity throughout a material, spatially discriminated. And we can also measure, for example, nucleation of cracks before they form to be true cracks, which of course, if you're doing forensic engineering or optimization of 3D printed parts, this is a huge upside. And then of course, on top of that, we can also do direct imaging, as one would normally do in a standard monochromatic beamline. So we can also overlay all of this information spatially, either in a 2D radiograph, or if we actually spin the sample in a 3D tomograph. So then we have, instead of having a few points in a system where we've had to step through, we are now ending up with, if I take this microphone, I can throw it in the beamline, I can see the battery, I can see the microphone top, I can measure the porosity in the microphone foam, and then I can look at the piezo resistor that is sitting in there, shaking, and I can also map the phases of the material. So that's very powerful. And it's also very intuitive. So it's more open to people who are not in the sort of physics domain, because the data that comes out is relatively easily understandable. Okay, so I mentioned Brgger imaging. What is this? Well, it turns out, as I've mentioned, if I have a sample in engineering materials diffraction, I hit it with neutrons, a few percent of those neutrons interact with the nucleus of the various phases of the material, and they shoot off, and we detect those in diffraction with diffraction detectors. And now you can imagine that means essentially there's that null space of those diffracted neutrons that if I now look at the transmitted signal, we're missing part of the signal. It's that part of the signal that before we were measuring. So if we now carefully measure the transmitted signal, then that is again equivalent to, instead of having peaks, now we have troughs or Bragg edges. And those Bragg edges, again, are indicative of lattice spacing and phase fraction. So depending on their magnitude and their position, we can get the same information. It's more difficult, but ultimately it's the same method, just in transmission. So what we can do now, instead of just looking at, for example, a single energy radiograph, if I do that, then I will see, you don't see my pointer, you'll see this radiograph here of this block that was 3D printed. Looks like metal, right? But now if I do a hyperspectral radiograph where I'm actually measuring and discriminating the energies of the entire bandwidth of the neutrons that I'm receiving, so it's equivalent to a color camera versus a black and white camera, right? It's the colorblind test. If you've ever seen the colorblind test and you're colorblind, you just see a gray mass. And if you see color, you see numbers, right? So this is exactly the same thing, because now here we can actually look at the disparity of the phases in parts of the print, and then suddenly, the word DOE shows up. So this is actually 3D printed with different phase content and phase fractions and strains in different parts of the print. So we're essentially looking at a optical manifestation of a disparity in phase content and strain in the material. So very cool, right? We're opening sort of a domain in imaging that we didn't have before. Now, what we can also do beyond this, so that covers the atomic lattice space. When we go to larger spaces, then what we can use is, for example, a Talbot-Lau grading. So grading interferometry is something that's been around for a very long time, but it has not been used specifically in imaging. So what we can do now is, if you look at the Scherer equation, essentially, you have an inverse proportion between the diffraction angle and the size of the defect or the repetitive order that you're looking at. So if you're looking at atomic spacing, then your diffraction angle is very large, say 90 degrees. But if you're looking at very large defects with respect to sort of the atomic scale, so let's say we have porosity or some voids that are inside a material that might be on the order of 50 microns or maybe 500 nanometers, then the diffraction angle of that signal is going to be very small. But with gratings, we can do interferometric measurements of that very small angle on top of just doing the normal imaging. So here now, we can actually map, again, spatially, for example, if you want to look at porosity in the field of, say, 50 microns, you can build a grating, or actually just tune a grating that is multichromatic, to actually then see those points of porosity. And again, you're superimposing this onto an imaging product. So you actually have a picture of the sample and you say, oh, here is my defect area, and I'm going to have failure in this area before I have failure elsewhere. Beyond that, we also have polarity and spin. We have spin of the neutrons. So essentially a neutron, even though it's a neutral atomic element, it does have magnetic spin. And the interaction with material happens to actually be, and this is just sort of a random case for each element, induces either a positive or a negative spin. So then that means if I'm looking at a multi-material system like those two sticks, if I just do monochromatic imaging, I can't tell those apart. But let's say that that's titanium and copper, which happen to be on opposite ends of the spin, then I can actually distinguish between materials that may be conveniently placed on that spin index just directly. So this is direct information. I'm not doing any high-end fitting. I just actually am looking at the full data that I'm getting out for my hyperspectral imaging. And then, of course, we can also enhance contrast, which you can see down here. This is from a Nature paper, because if you put a wasp into an imaging beamline, apparently then you get published in Nature. But what you can see here at the edges is that you actually get contrast enhancement of the material, because you actually get an edge effect where you get small angle diffraction at the edge of the material. So then that actually allows you to see where there's a change in porosity density or diffraction index within your material. So the fact that you get that slight angle change of your signal actually allows you to increase the contrast of your material. Okay, so that's the methods. Now, where is this useful? I've already mentioned the microphone as one example, right? So if, let's say, we have a lithium cell, an industrial lithium cell, that's a perfect example because we can actually take the cell, we can raster it, and then we can say, well, let's look at this cell under charge and discharge. Now, during that charge and discharge, we can do Brgger imaging, and we can actually see the different chemical lithium components and the different phases of lithium carbide. And then we can also measure the stress in the cathode as the cell is charging and discharging. So we're getting a full picture of this battery's behavior. And of course, now if I do neutron grading interferometry on top of this, we can also start seeing cracks in the cathode wherever it's starting to actually nucleate. So the idea is that we have a dynamic system that can essentially grab all of this information all at once. So I can actually do charge and discharge cycles in the beamline and actually see this thing break or perform, as it should. For the mechanical engineers in the room, of course, 3D printing and also functionally graded 3D printing is a huge field. And there, of course, we have a lot of constitutive model benchmarking that needs to happen. If we are building, for example, in this case, this is a small Arc de Triomphe that was done by Anton Tremson, where he actually 3D printed those little samples. So this is in the spirit of Airbus, for example, which does now failure critical parts using 3D printing to save weight. But at that point, you really have to understand your cooling mechanisms and the residual stress mechanisms in your materials so that you have good quality proofing algorithms to back up, also backed up by experimental data to back up your designs, especially as they evolve. Now, probably as a structural engineer, the most enticing capability is just doing neutron grading interferometry, NGI, on, for example, fracture samples. So what we can do here is, here we have P, the autocorrelation length, right here. That is essentially the spacing of the grading. So you can tune your grading to the specific repetition length of your defect to say, well, I know that nucleation, say in 316 stainless steel, generally occurs at the 2 micron level. I can build gradings, throw them in the beamline, and then you can see on this dog bone sample initiation of fractures essentially in the nucleation stage. So at that point, there's no visible fracture there. This is just nucleation. That, of course, is very powerful. Similarly, we have concrete, which is a multi-scale material. Here we have porosity at various levels. There's especially also, of course, this is from a DOE perspective, they have a strong initiative in this field because they need to ensure that especially light water reactors and general nuclear cladding concrete really performs well over 100 years. So understanding early phase behavior and being able to map that into a long-term performance is very much in their interest, but of course, so is for major infrastructure to understand how the porosity, for example, of concrete evolves over various length scales, seeing infiltration of chemicals. This we can map again in 3D. Similarly, we can do the same thing with plants. This is a lot of fun because if you do this in X-rays, normally you actually physically fry the plant because the X-ray beam is photons. Photons have a lot of thermal energy, but with neutrons, the sample in the end is mildly radioactive, but is not thermally actuated. So it's not mechanically actuated either. So we can actually watch water go into a plant structure. Similarly, we can look at soil aggregation and understand, again in 3D, the structure of soil and various nutrients, because we can distinguish those nutrients, again, through Brgger imaging, but also through neutron grading interferometry. And another large field is that of high-end implants in the medical field. We have orthopedic implants, we have dental implants, and there's a push by the large industry players to be able to 3D print custom implants for patients, right? And there again, we need to have a very strong validation framework and benchmark tests of those 3D prints. So now we're not looking at a unique 3D print, we're looking at a catalog of 3D prints and probably some linear interpolance in between those 3D prints to understand their reliability. But beyond that, there's actually now a push also in the 3D printing world to create and to design porosity at the interface between the human tissue or the human bone and the implant. And the goal here is to make that as gradual a transition as possible by actually increasing the porosity and increasing the surface area of the implant on the implant surface where it needs to fuse with the bone. So the higher surface area not only provides a cleaner interface and fewer stress concentration points, but it also actually increases bone growth because bone grows essentially as a function of the surface that it encounters. So the more surface area you have, the more it's actually willing to graft itself onto a foreign object. So this is a huge push, especially in reducing the number of failed restorations, which account to apparently about 10% of expenditures in healthcare. So that's significant. And of course, as civil engineers, we can similarly combine these capabilities to understand corrosion processes in samples. So they can be samples that are actually being stressed and corroded in what physicists will call an in situ environment, meaning that they're at the lab. They have to, unfortunately, be at the lab. We cannot do this in the field, but if we have a sample, for example, we can look at hydrogen embrittlement. We can actually map the hydrogen front. We can also look at strain and phase evolution as well as corrosion products as they infiltrate the steel substrate. And of course, early crack detection. So this still is, quite powerful. Now, what does this look like? This is a typical beamline. It always is generally a pie slice because our source is over here, comes in through a guide there. And then we have a large cave with advanced optics where we can actually do testing at various fields of view and various sizes. So essentially, again, more or less, this is the same thing as getting a CT of your head. It's just instead of using photons or magnetic resonance, we are using neutrons. And really, again, our big plus is that we can penetrate engineering materials like metals easily, which is something that X-rays cannot do. They're not reliable. So that's sort of my baby, but now I want to show a fun example of what we can do with neutrons and maybe where the challenges still remain, which is, if you're a GoldenEye fan, you've probably seen this video before. But we have the Aresiva Telescope in Puerto Rico, which is a colony of the United States. I'm going to get in trouble for saying that. It was built in 1962, and it was the largest such radio telescope until 2016. It actually was not a passive telescope. It was actually also a radar transmitter and receiver. So it was used also by the SETI program for extraterrestrial life and by radar telescope people to map the moon through active transmission. And that is what that large dome is. That is actually a radar transmitter. So it's quite a heavy system, but it's fully suspended by the same systems that we know from suspension bridges. So this large catenary system that in the end, after multiple upgrades, is quite complex. So if you look at this, the original structure was built in 1963. And since then, through various upgrades, this is an NSF operated and owned piece of equipment, the weight of the transmitter actually doubled. And during that time, additional wire ropes were added. And actually also the tie-down systems that you can see here were upgraded multiple times in 1973 and again in 1997, where at the end, there was an active tie-down anchor system that was hydraulically actuated that actually holds the system down. And that's not for wind safety or, for example, hurricane safety, but that's actually just to maintain the same distance between the receiver, transmitter, and the dish due to thermal effects, because during the day, the ropes get longer and the telescope sags. During the night, it actually comes up. So for the various radio measurements, they wanted to keep that stable. But of course, as a civil engineer, when I start seeing this thermal effects and somebody tying it down, this sends up warning lights. How was this tied down? Well, it was tied down with these typical wire ropes, as you would also find, for example, on cable cars. They're slightly different, but ultimately the same beast. And they're terminated in this case in these spelter sockets. And these sockets are literally just a steel wire, which is broomed out mechanically, manually by hand, and then filled with just elemental zinc. So you essentially have more or less these super high strength steel wires held together by bubble gum. And if you fan out those wires properly, then you essentially get a hydrostatic stress state in the zinc, which then makes it more or less quasi-incompressible and makes it hold its shape. So this is stable if done right. And this is also very common for elevator ropes and, of course, for suspension bridges, say, built after World War II. Now, this telescope, and this is essentially to scale, you can see, is hung from 3 very large towers. And during the upgrade in the 90s, that's when the telescope's weight was increased significantly. And these extra sets of wires were added, and they were actually added eccentrically to the main anchors, mostly to provide torsional rigidity of the telescope. But of course, by doing so, they did change the structure and the load significantly. It only had a design safety factor of 2.15 or 2.25, so that's quite low. So they went into this being quite lean already. And then in August 2020, of course, they had their first failure. And this was at this point already a very old and worn facility. And at that point, the forensic engineer, Thornton Tomasetti, was brought on site, and they started to do a design for the replacement. But as that happened, the next wire, just a few months later, MN44 failed, and then 42 failed shortly thereafter, causing the catastrophic collapse of the telescope. Now, luckily, because there were already previous failures, the site was fully evacuated, and there were cameras. There were cameras trained on this. Now, actually, we'll see a drone shot. This is incredibly fortuitous, but the forensic engineer had actually hired a drone operator to hover over the towers because they started seeing failures of single wires near the spelter sockets. And luckily, we actually have footage now of the failure. There was also some acoustic emissions and some other NDE actually stationed up top. That's the NDE box right there. You can see now we have wires that have already spalled off the outside of that cable. That is the cable that will fail in now. And it just pulled out of the socket and then took all the other wires with them. Operator is awesome because they actually turned the camera to watch the antenna land. So this happened. Thornton Tomasetti was essentially already on site, and they said, well, I remember Adrian did something about cables at some point. Maybe he got his PhD in it, so maybe we'll ask him to help out. So they gave me a call and they said, well, can you participate in this investigation and maybe provide us with some information that we would not otherwise get using just traditional methods. So, of course, through traditional methods, you could see very easily that it was that third wire there that just literally pulled out of the socket and just essentially ripped the rest with it. So the question is, why did this happen, right? So what we did is we said, well, we could take a spelter socket component, so a slice, this is 24 millimeters of that, it's one of those failed sockets, or this is not the one that failed, but it's an immediate neighbor. And we can do radiography and just understand the as found condition, because actually just cutting these with a saw, the stiffness and the strength disparity between the zinc and the steel is so high that you disturb the contact features and the configuration of that sample significantly just by slicing it. So we said, well, we could take a slice and then look inside and see what we find. So we can do tomography, et cetera, and do 3D models of this. So this is now M8N, which is one of 2 samples that we had, and it's the well-behaved sample. What does that mean? Well, it means that we detect essentially no major artifacts. There's no delamination, there are no bubbles visible around the outside between the wires, the steel wires and the zinc, but we do see a little bit of pullout at the ends here. This is not a scary amount of pullout, but this means that there was some plastic flow, which we cannot measure directly through BEI, but we can see it. There's some plastic flow of these wires actually pulling out, right? Otherwise, there would be no gap. Similarly, when we did some tomography, we saw the same area. We could also now map it in 3D because you can get a mesh of your system. So you can get a mesh of your zinc, you can get a mesh of your steel, and then sort of the air is the void. Then we looked at the one that was in trouble, and then we saw something very troubling, which is massive pullout for the outer wires, but only the outer wires. And actually, deformation for the middle volume, which you could see from the outside, but this pullout was very interesting. So we saw this preferential slip on the outside, and then essentially the middle piece just pulling down. Now, we also wanted to do Brgger imaging on this, but unfortunately, the zinc structure and the zinc crystals were so large, you can see them. There's sort of these black clouds that show up in this image. This is now rastering through the various frequencies of neutrons. So it's like looking at the different colors of light. Unfortunately, those made reading the residual stresses using Brgger imaging in this sample, I wouldn't say impossible, but at this point, very, very difficult. So what this means is that we'll actually go back and do traditional just point-to-point diffraction to understand this. Now, since this is sort of a show and tell for civil engineers and structural engineers, what caused the failure? Well, it turns out it was actually just poor socketing. The team looked at corrosion, they looked at wire breaks, there was an acoustic monitoring system, thermal effects of the dish actually raising and lowering. Turns out that was within design specs. Now, what did contribute is that hurricanes did overstress the system at regular intervals, or I would say irregular intervals. And there was a low design safety factor up front. But ultimately, what killed the system is that the brooming of the wires, the socketing was not done in a methodical fashion, and that the inspection team did not understand that seeing this much extrusion, this is actually the cable failing slowly, this much extrusion of zinc out of the socket is a massive alarm sign, and was also in the standards to be known that if you're losing more than 1/6 of the diameter of your whole system, then you're essentially in progressive failure. This was cataloged and photographed, but nobody thought to actually act on it. So that's why we have the photos. They took photos, but they didn't do anything. So essentially, in the end, what happened was that because we don't have those wires actually spanning the entire socket volume, that truncated conical bore, then we don't have a hydrostatic stress field inside the zinc, but instead we have a highly deviatoric stress field with massive shear along those lines. And what happened was that this column was slowly extruded out of the socket and then pulling with it or fracturing the wires on the outside. That's why we saw that preferential slip of those outer wires in even the sockets that had not failed, because they were essentially without fail, they were all poorly socketed. So in the end, what this taught us is, again, and also for me as a PI of engineering materials, Beamline, which is essentially an applied physics instrument, is one of the biggest lessons that I'm learning as we're developing this thing is that physicists generally are the owners. In this case, I'm the weird one because I'm technically a civil engineer who now has a Beamline, which is unusual. But because of that, I understand that the overlap of that initial capability and the ownership of that technology to the customers of that technology really decreases rapidly as we go to more industrial applications. Material scientists generally still understand some level of diffraction because they learned it in fundamental physics. Engineers starts to get a little more shaky, biologists, scientists, etc. Similarly, once we get to medicine, they don't have a clue, right? And then we go to archaeometry, conservation of historical objects. They're just in their own vector space, right? they're not scientists in the sort of intensive definition. So this is a very challenging group of users, but the idea is that if you have high throughput instruments that are very capable, that also provide well benchmarked results, we can have massive impact because the capabilities that are here are incredible. So if we can actually deliver these capabilities to these scientific fields, we can do some very cool science. And that completes my talk. Thank you.
Thank you very much. I will open the floor for questions. Maybe we'll start first from those in the room, which is easier. Any questions for Adrian? Yeah, go ahead.
Yes.
And to correctly use the non-stress grid as a baseline.
Yes.
How do you get this baseline? Because I mean, you have a bridge, you cannot get the tendon not stressed, take the baseline and
Yes.
it again.
It's a very good question, and this is, I mean, in any residual stress measurement, that's always the sort of the art science and the voodoo, right? Of where you start. What is your sort of D0, your unstressed lattice parameter that you consider to be healthy or zero or whatever you want to call it? Here, normally what's done is you actually take a piece of your sample and then you cut with laser EDM, for example, laser or just EDM, electron discharge machining, you cut a comb into the sample and then you measure that comb, and that comb is then stress-free, close to stress-free. So that's sort of the traditional by the book method. The other method that we used in the BEI example here is what we would do is we take an average reading of a wire that is, for example, free of the socket. So we know that the mechanical boundary conditions are essentially zero, they're air. And then, of course, you have the issue that the residual stresses in that wire are massive from the cold drawing. So we have, you know, the outside versus the inside of the wire. You may have massive compressive stresses on the surface. You have a tension stress in the middle. But if you then measure, and you're careful to actually measure an inclusive section of the wire that takes into account the symmetry, then you get the average stress of that wire free of external forces. So that would then be your D0, but you have to be very careful.
Let me also open the floor for questions from the online audience. So you can simply unmute and ask a question if wished. Because we cannot easily see if you raise your hand. But let me ask you what we were discussing before. I think important for many engineers is the definition of stresses or residual forcing elements within the material. And you were explaining, you also mentioned it here, but it would be good to stress a bit what is the separation that can be achieved through the neutron diffraction. The fact that you always get the elastic portion.
Yes.
And then what does this mean for our characterization?
Right. So no, it's a very good question. So when it comes to residual stress mapping, I mean, the power of, as you just mentioned, of really time of flight diffraction or diffraction in general is that we can deconvolute the plastic from the elastic domain, because essentially we're only measuring elastic strain. So we're the truly elastic strain potential, the lattice spacing of your system. So there's, first of all, since we were actually doing an atomic measurement, we first have to understand the material and the multi-phase behavior of the material to understand which phases of that material have micro or sort of nano strain behavior that can be mapped to the macro level. So in the case of steel, it's generally the BCC ferrite phase. We've just found that has, if we measure the BCC ferrite phase, then body center cubic lattice parameter, then that is largely essentially maps perfectly to your global strain. So here, the beauty is if you have a residual stress, for example, due to plastic deformation in an area in your system that then creates some incompatibility that then during unloading, you get a partial hysteresis loop, then what you can measure in the end is the residual elastic strains left in the material, irrespective of what plastic flow happened in that material. So you get a very clean understanding of the actual strain potential in the material. So if you cut the sample, you would see that deformation spring back. So if you're just doing traditional slicing. So this is where, because sort of the slip mechanisms and dislocation mechanisms of plastic deformation are entirely different from your elastic strain behavior, you can actually fully, and you're blind to the plastic side, but because of that, you can fully deconvolute the system if you have, for example, other surface measurement of either using, you can use videogrammetry, you can use a DIC or just traditional strain gauge grids. Then you can get the full strain on the surface. You can get the elastic strain on the surface with neutrons, but then you can also get the elastic strains inside the body of the system. And of course, the holy grail right now, and this is not fully realized yet, but people are working on this, is that in the end, what you would want to do is you want to take your, say, monolithic material that has been 3D printed, you want to stick it into a goniometer and then actually be able to spin it, take multiple reflections of it, so just multiple shots at different angles, and then reconstruct the full strain tensor. So tensorial tomography is something that has not been, we don't have a general solution. If we have very clean boundary conditions, very clean sort of assumed loadings, we can get pretty good at this. But if we're just looking at residual stress fields that are not well defined outside of sort of a boundary condition driven system, then that's still something that has not been achieved. But that's an area where AI is now being employed. We're hoping we get something.
One more question for me. Another thing I was wondering about is, there is now this sort of trend to discuss data-driven mechanics, where if you have full field information, usually from imaging, and this is what we do also now with the Yogos that I was trying to explain before, maybe you can use it for updating and inferring constitutive material laws. But for doing this, you need dense information. That's why doing imaging. Can this sort of information serve such a purpose?
Absolutely. Yes. So it's actually the sort of AI and machine learning is being used also in optimizing the actual tomography
Configuration.
so you're actually, it used to just be sort of a golden ratio open loop system where you just take a bunch of reflections and then you try to build, you fail or you succeed. But now with machine learning, you can actually optimize the minimization of the kernel as you're actually running these reflections, and the ML will tell you which reflection will best reduce your error as you're going, and that in itself has reduced the time also for the reconstruction. But let's say you just build just a sort of brute force 500 reflection model, then that gives you very dense information.
What is this resolution that you can achieve when you say dense?
Good question. So spatial resolution is, well, the perfect optical spatial resolution is 50 microns. But then with divergence, et cetera, you're about at a pixel size of 100 microns by 100 microns. Mm-hmm. So you get one information set, all of the whole hyperspectral imaging information for every about 100 microns. Okay. Now the PSI has a neutron microscope, which goes down to 5 microns, but the field of view is essentially like 5 millimeters.
And the size of the specimen you can test, because that was also.
So the size of the specimen for the Vulcan beamline, which is a static beamline that is coming online next year, is 20 centimeters by 20.
Okay, so a regular testing, and what you would do for material.
Yes, so we can also put a load frame into the beam essentially,
as long as it scales.
Yeah, I mean, yes, but you can have spinning load frames that actually spin. Essentially, it's like a torsional load frame, but instead of applying torsion, you're actually just using it to spin for tomography. Mm-hmm. So you can do, 20 centimeter by 20 centimeter sample is quite big. Right? So then you're actually looking at some serious.
What you would extract also for destructive effects.
Yes, okay. Exactly. Yeah.
Good. Are there any more questions for Adrian, either in the room? Yeah, go ahead, Paul. And then if someone online, again, just.
Can you transport them to bridges to do
It's a very good question. Unfortunately, no. So this is our biggest problem, is that you need a thermonuclear fission reactor or a particle accelerator, which is 1 kilometer long. So in both cases, highly impractical to bring to a bridge. And actually, even if you were to bring it to a bridge, the problem is that the method does activate the sample. So it does make it mildly radioactive. Now it's activated, not contaminated, which means that if I put my cell phone in the beam, depending on what materials, constituent materials make up the cell phone is then radioactive. I can't take the radioactivity off like I could from a powder of plutonium, right? But it's radioactive. And that means that we have to let engineering samples cool down for a few months. Normally it's about 1 to 4 months afterwards until they're safe again below detectable limits so that they can be taken out again. Now there is,
not, I would say.
Los Alamos is working on laser-based portable neutron sources. So
with
they
minimal radioactivity, like what would be the
it's still the same results. It's just that they're Los Alamos. That's sort of what they do. But the idea is that it's essentially about the size of a truck, and they have a pulsed high energy laser that actually shoots into a target of plastic, and then that plastic falls off the neutrons, and those can be used very close to that laser. So they're 2 orders of magnitude lower in intensity and flux than what we have at a source like this, but because they're so small and we can get so close, then we can work
But you
with it.
cannot wrap, I mean, it has to be, don't you need somehow the specimen to go inside this truck, right? So you cannot.
You would, no, technically you could put the beauty of imaging sensors, unlike diffraction sensors have to be at certain angles off the sample and they have to be perfectly aligned. An imaging sensor looks like this box. It's just big
So
and
you can also
expensive,
just
but
in
you
a
can
distance.
literally just take your sample. If this is my neutron cannon, I could just move the neutron cannon up to my sample and then just put my imaging detector behind it. And poof.
So it's.
But then, of course, the sample is radioactive, so that's the downside.
I see.
Yes.
Interesting concept. Any other question, maybe from our online audience again before we conclude the session? I don't hear someone popping up. So what I'm going to ask you is just leave us with the message you would like to close with for. Oh yeah, go ahead.
So you also showed an example of plants.
Yes.
How they sucked up the water, and it was like stream basically.
Yes.
Were those plants live?
Yes, they are.
Because
So,
then afterwards they're radioactive.
correct. They are. So this, it's a very good question. So something I didn't mention, I mentioned very quickly is, first of all, normally we need contrast in imaging, right? So in the case of X-rays, it's also attenuation contrast of density of materials. Here, the contrast has more to do with the Z number of the specific element. And it turns out that hydrogen is one of the strongest attenuators of neutrons. And that's why we can see the water go up into the plant. But yes, this plant is perfectly alive and it's perfectly radioactive afterwards. But so it may get plant cancer at some point, but sort of in the name of science, we can put plants in a neutron beam. We cannot put live animals in a neutron beam because of animal protection. The bee that you saw was a dead bee that was imaged. But I think there have actually been a few insects that have been put in a neutron beam. So insects somehow are not, I've heard from many people who work with animals, they say if it's fluffy, you can't touch it. If it's a bug, you can get away with it. So they've shown wings flapping of, I think, of a bee.
What if it was a very slow process, because you said across time scale? So if you wanted to see how maybe a material grows,
Yes.
if it's let's say alive somehow, if it's a live organism, you could have it in the diffractor for weeks, for example.
So the issue there is just the cost of producing neutrons. So technically you could.
But
yes.
it's very expensive.
So the idea with especially CUPI²D, my beamline, is to take that exposure length, that one photo, right, one radiograph, down to seconds. Right now, that's minutes or sometimes hours for weaker sources. But if we can get it down to seconds, then we can look at really actual dynamic results.
But if you don't care about the dynamics, but something slow, it's already configured to do that.
Yes, so that it can do now. So the only question is, can you afford the beam?
Yeah.
So exactly. So there are, for example, weaker reactor sources at various just university-run facilities where they say, well, you know what? Okay, we may not be as full, or we're capacity constrained by the personnel rather than the neutrons. Then they may just say, okay, throw it in the beam for a month and watch it grow. So you get crystal growth, for example, you
It's
could,
done.
and protein folding, something that I didn't show because it's not imaging, it's more pure small angle scattering, but pharma has a huge interest in actually watching the proteins fold, and they can get, again, sort of indirect phase information on the dynamics of those protein folds. And the beauty is, because neutrons in this case, they're either thermal or cold, which means that there is no thermal activation of your sample, right? This plant had no idea it was in a neutron beam. If you put this in an X-ray beam, then the X-ray beam, especially if it's low energy X-ray, it's counterintuitive, but if it's low energy X-ray, you will literally catch this on fire in like 5 seconds and it will just combust and be gone. But with neutrons, your interaction with the actual
Is minimally
plant is
invasive.
essentially, from a mechanical and chemical standpoint, is zero. From a nuclear standpoint, you create unstable isotopes somewhere in the lattice, but from a mechanical standpoint, it's irrelevant.
Okay, the last question, because now we have more than we can afford.
It's wildly different, and it is a function. So water normally is not a big problem because it's just an attenuator. It just absorbs the neutrons and it creates heavy water. But it depends entirely on it. There's an activation chart, and just especially for metals, it's very unpredictable because it's normally trace elements in the alloying that are highly sort of big bad actors. Copper is bad, manganese is bad. There are a few. So if you have a stainless steel, it will activate. And then, of course, there's a question of both peak activation, but also half-life of that specific isotope. So aluminum, for example, is red hot, as in not thermally hot, but nuclear hot after exposure, but its half-life is essentially, a few minutes. So you just wait 10 minutes and it's already at 10%. Manganese, etc., can take months to decay. And then it's just a few, it's literally those few manganese atoms in there that are red hot, and you just have to wait for them to calm down. So it's sort of a broad spectrum. But if you're interested, there are activation calculations that can be run very quickly to see, am I talking about a week? Am I talking about a year? So somewhere in there.
Good. I think with this we can conclude, as we're
Yes.
officially over time. Thank you very much, Adrian, for this talk, and we hope to have you again soon. Hopefully, also within our regular semester. So
Yes.
again, many thanks.